if there's no friction, then when the bar makes it down the incline, we talked about the incline yesterday, but the bar makes it down the incline, conservation of energy is how we would express the speed of the bar when it's here. That part's immaterial. The bar just needs something that would have given it velocity so we can go to this next portion of the problem, which is where the problem, I believe, gets interesting. So at this moment, for the time being, I'm going to use just a lowercase v to indicate the velocity of the bar, but it should be made clear that the initial velocity of the bar is the square root of 2gh. So somewhere towards the middle of this problem, if you were actually doing this problem on the exam, you would likely have to do this substitution. So it's something to keep in the back of our mind, but this is just the initial velocity. Our velocity is going to change once we enter this region of space where there is a magnetic field. Now, you have some choices on how you proceed from here. One of the first things you could do is you could just use motional EMF to figure out the direction of the current and the direction of the force on the bar. I'd rather use Faraday's law. I think Faraday's law is a little bit more powerful, but also you might be expected to show Faraday's law under a certain circumstance. They can say, use Faraday's law to derive an expression for the force in the bar, and you would have to use Faraday's law. Everybody got that? So I'm going to start with assigning a variable to this, even though a variable isn't necessary to do what we're going to do. So they don't have to give you the length of the rails. All we need to know if the rails are sufficient for the bar to slide long enough for us to get the data or get the expression we need. So assign something here if you don't have something. I'm just going to go with x for right now. And I'm going to give myself a bit of knowledge of the future that v is going to be equal to minus dx dt. It's minus because it's moving to the right. And if we look, it's making the area smaller. Now, this minus sign isn't going to matter in the long run, but it's important to be considerate of direction in these problems. And since we know later we're going to be taking an integral that's related to the area, and then taking the derivative, which is related to time, knowing that the area that's being that is been created by this bar is getting smaller, is going to be related to that negative sign specifically. Do you follow what I'm saying? We're comparing x with v. And so, and this area is getting smaller. Now, we do need an expression for the flux if we're going to use Faraday's law. And our expression for the flux is still the integral of b dot dA. But I think we can all pretty well agree that this is ornamental, meaning it's nice to have this fancy expression, but the area is just the area of this rectangle, and the magnetic field is constant. There's no dependence of the magnetic field on a particular location of the area. Does that make sense to all of you? We're trying to find ways to increase how quickly you can employ certain rules. So this portion here, you have to ask yourself, is there any dependence of the magnetic field on a particular location of the area? If there isn't, well, then you can probably pull the magnetic field out of your integral. And then ask yourself, is there any dependence on the direction of the area and the direction of the magnetic field? In this indication, the answer is no, there's no dependence there. We know that the area and the magnetic field are perfectly aligned. So you should be able to drop down in one line and say BXL as your flux. There's no reason to make it more complicated. Only if the magnetic field is different in the area in which you're taking the integral do you even have to really be phased by this integral. The only other way that this would come up is if you have a weird area or a weird angle. But if the magnetic field is uniform in that region of space, you can probably jump from the definition of flux right to just taking the magnetic field and multiply by the area. If you're trying to write yourself notes, that's what I'm trying to get at. Again, so if you're trying to be better about this integral will only matter if there's some dependence between location and the magnetic field. Otherwise, B times A, and be done with it. Now, we have to work in a variable that's going to be changing due to the velocity. That's why I'm working in a variable that I created, x, because we need to have that variable. It's related to what's happening here. Now, going on to Faraday's law, because this is just our first step in Faraday's law. Faraday's law is minus n d flux dt. How is the flux changing? Well, the area is changing. We know that. Now, there's only one loop, so n's going to go away. I'm going to leave the negative sign there because the negative sign is a reminder to me that direction is going to be important, and we will need to come up with some information about direction, but we're just going to sub in our flux here. So when I sub in the flux, I'm going to get minus d dt of bxl. Well, the bar doesn't change size, the magnetic field doesn't change its value. The only thing that's changing is x. So this becomes minus bl dx dt, which we've already put in there is minus the velocity. So this is where you get your BLV. Okay. Any question to this point? All right. It's on you. I want you to attempt to use Lenz's law to justify the direction of the current in the bar. So by stating Lenz's law that there is that the flux is being reduced, so the generation of the current is to reinforce the flux that's disappearing, that I think gets you the 2, maybe 3 points for justification for Lenz's law. And then when you're done, indicating that the direction of the current is downwards through the bar. I think that's, make sure if they tell you to do it relative to the bar, do it relative to the bar. Now, the next question I would ask is for you to find an expression for the force on the bar. And this is where this problem gets interesting with the math. So you guys who are my mathletes a bit, this is where I would hope you would perk up. So find an expression for the force on the bar, please. If you don't know where to start, I will start you. That has to be it. But you can't have I in your answer. So you need to get rid of I. Shouldn't be hard. You have a resistor in a single loop circuit. So your very first substitution is likely to use Ohm's law. But you can't have the EMF symbol in your answer. It's got to be based on the physicality of our apparatus. So you'll have to sub in for the EMF BLV. All of this substitution takes place here. Plus the cross product, but I think we can handle the cross product as being 90 degrees. We'll be okay there. So this is the substitution I'm looking for. Any questions? Now, you mathy folks, 2 things. Convince yourself the direction of this force is to the left. It has to be. Something's trying to stop the bar from moving. We're not generating a current for free. But also, this has to equal MA. You guys who had in mechanics last year know that this is the first order differential equation. of which you should be able to solve it. I'm going to assume that maybe we need to review that tomorrow. Today we worked this problem to this portion of our conclusion. There's a mistake here, and it's not that it's a mistake so much in what we did, but an omission, and we probably should talk about the omission. So if you'll get to this part in your notes, I'll be ready to go in just a second. Are you all ready? All right. The omission is this. When we get to this point here, and I'm going to just back up a little bit, everything until we get to this point used what we've talked about in E&M. And so it was very much, that we have a velocity for this object, it reaches these rails, there's no friction, it hits the rails, it's moving to the right already due to a process that happened before. And that process that's before, doesn't matter now, we are here with some initial velocity. The bar is moving to the right, and because of this scenario, because it's a closed loop and because of a magnetic field, we have a change in magnetic flux. And that magnetic flux change is going to cause a current to run through this particular loop, but the current, as it runs through the loop, interacts with the magnetic field. And that interaction applies a force to the bar. Now, didn't talk about this in any of the other things we've done, but no matter which version of Faraday's law we're dealing with, whether it's this one, which has clear motional EMF, whether it's changing the magnetic field and letting a EMF develop, or rotating the loop in the magnetic field, there's going to be some version of Lenz's law and an interaction with the magnetic field that's going to require external work to generate the EMF, no matter what. The one where you just switch off the magnetic field and you generate an EMF, that one doesn't appear to have work. Let's see if we can do physics for a change.
You said there's prime real estate up here.
I did. I offered your seats off to other people. There's prime real estate in the front. I'm not wrong. Look, so if you'll recall, the original way we generally set up differential equations was to use Kirchhoff's rules. And we would try to work in, or we'd have something where there'd be a Kirchhoff's relationship that would have current and charge in it. But creating a differential equation is not as complicated as it sounds. All you have to do is introduce a differential into your equation that is related to other variables that are already there. So we have an unbalanced force that's acting on the bar. That unbalanced force is acting to the left. And it's due to the action of the bar interacting with the magnetic field. And as I was trying to say before, in every version of Faraday's law, there's going to be some way in which energy is required from an external source in order to generate this EMF. And it's going to require external work if you wish to maintain it. The only one where that's not obvious is the one in which you just switch off the magnetic field. And it should be obvious, the external work is probably coming from whatever's generating that magnetic field. We're just assuming that nature has one and we turn it on and off. You guys understand that that's not how it works, so the work was happening there. But if you try to flip something in a magnetic field, you already know this because when you guys are playing with your motors, did you notice sometimes when you went to go mess with it with your fingers, you could feel a little bit of resistance in the motor when you're trying to get it to flip over on its own? Like maybe you were pushing it in the wrong direction and it tried to flip it back. Well, when you were doing that, you were actually generating an EMF in that loop, and it was turning the other direction. So if you are interacting with the magnetic field in this way and you want to flip the loop, there will also be a torque on the loop to try and prevent you from flipping it. You're going to have to provide external work on the system in order to generate this EMF. Now, for this bar, if there's no external force on the system, if there's nothing to maintain the velocity, then the kinetic energy of the bar is going to slowly be reduced due to this force until there's no energy left. Now, it can be shown, and I don't know that we will do this today, but it can be shown that the total energy dissipated in the resistor will be equal to 1/2 mv squared of the bar. I'm saying this to you, which is worth writing down, because one of you on our next test, if this shows up, will likely attempt to integrate the power equation with the function we're going to get from the end of this particular bit of work. And it will be a long, drawn-out process because you'll have to integrate work as a function of time for some logarithmic or exponential equation to basically show that the total energy equaled 1/2 mv squared. When you can jump right to it, the total energy in that resistor will be whatever energy this bar has. We will do this as an exercise, but energy is going to be conserved. In this circumstance, this force is a conservative force because it's from the electromagnetic force. And therefore, the amount of energy the bar received from gravitational potential energy earlier is now kinetic, and that kinetic energy will be dissipated in that resistor. You want to go back far enough, and if the problem were like this, you might have to say that the total energy dissipated by the resistor will be mgh. I promise, the math will work out. The one thing that, this one. We have this is an unbalanced force. And although I know I'm dancing around semantics, what we're trying to say is there's no external force pushing on the bar to keep it moving. There is a force from the magnetic field pushing on the bar to try and prevent it from moving. Do we understand that? That means this is going to lead to an acceleration. But this is the omission from yesterday. This acceleration is going to be in the opposite direction of the velocity. Inserting this negative sign isn't accidental. We have to recognize the force is to the left and the velocity in this function is to the right. If the velocity were squared, that would strip away that portion of the vector part. But force is a vector, and it must get its vector information from something in this function. And it gets its vector information from the velocity. What we're trying to say is either the force is in the opposite direction of the velocity or the velocity is in the opposite direction of the force. One of those has to be true. So we're going to insert this negative sign here to recognize that we know the force is in the opposite direction of the velocity. And I'm putting it on the MA side because that's where the force is. So we're going to begin our process right here. This is not the differential equation. To get the differential equation, we have to insert a differential into this. And the differential, of course, that we're going to use is that the acceleration is equal to dv dt. Now, hear me out. I know that you'll be taking the exam one day and you'll be trying to find ways to make things go faster, and you'll want to skip steps and stuff. And having graded your test just recently, a lot of you do. Your brains are working and you're skipping things. The word derive has a pretty heavy burden of proof. There are things you can do to make this go faster. One of them is not writing b squared L squared over r the next 100 rows. So it is okay to temporarily say, look, I got a complicated constant, but it is a constant. So for the time being, I will use this constant. But you can't just define the constant here and leave it in your answer. At the very end, you will have to substitute that constant back in. I would encourage you, though, if you want to save time and to streamline your algebra, because some of you will make algebra mistakes in haste. This will help streamline your algebra. So I'm going to write C. In fact, I'm going to say this is the part where we have a differential equation. So C times V equals negative m dv dt. Now, I've given you these steps already. All I'm going to do is say them out loud again so that we review them because we haven't done one of these in a while. We use only one process so far for dealing with differential equations, and that is splitting the derivative. And the only reason we're actually able to do it in most circumstances is that when we split our derivative, we create two separate integrals that aren't interrelated, meaning there's no other variable related to t or v. So when we separate them, the side that has v is exclusively about v, and the side that's about t is exclusively about t, and there's no internal variable that's related. Now, if you guys go on, all right, so split the derivative. So I'm going to multiply both sides by dt. That is our first step to split the derivative. Collect terms, which means to place anything with v on the same side as v and anything with t on the same side as t. So we only have one variable to work with here, v. So I'm going to move v to the other side. I'm going to look a little bit to the future of what has to come next. And if you'll recall, in the past, any function that's looked like this has produced an exponential. I'm expecting something that decays. Wouldn't you expect that too? That it's going to slow down. I don't expect the velocity to increase without bounds. I expect the velocity to slow down. So I'm going to actually move the m and the negative sign over to the side with t. And that's just looking at the future. You don't have to, but this will make your math go a little bit faster. So I'm going to move the m and the negative sign. That also leaves me with a very clean function on this side, right? Because this is the side that I have to integrate. I'm making it as clean as possible so there's less distraction. All good to go? All right. Integrate both sides. I think it was Sean that asked a question yesterday on the way out. What do we do about like if we do this and we get a constant, can we plug in the initial velocity for the constant? Yeah, you can. You can do this as an indefinite integral. AP will accept it as an indefinite integral as long as you manage the constant the way you guys have been taught to do so in calculus. I don't, because in all of my reader notes about the exam, they check to see that you set your limits appropriately. So I'm going to go by the notes that I have. But if you deal with the constant by putting in your boundary conditions after the fact, that's just fine. And if you're comfortable doing that because that's what you've been trained to do, go ahead and keep doing it. Don't change. Does everybody who's taking calculus understand those statements? So I have a few that clearly don't. But how many of you are in calculus have done an indefinite integral? Okay, so that's all of you almost. So you understand that when you're done, you put a big C there to indicate that there's a constant, and you have to put in your boundary condition, which means you put in a value for one of your variables, and the C ends up being whatever the result of that constant is. Now, we are going to do definite integrals. I'm going to say at time 0, the object begins with a velocity of the square root of 2gh. I'm establishing the boundary condition now. It will serve the same purpose as putting in your boundary conditions later and leaving the constant there. My upper bound is just going to be an open function, t and v. I'm looking at some v in the future and some t in the future. Because these are unconnected, I can do both integrals separately. The left side integral, pretty straightforward. It's just going to be t. So I don't think I have to do the dance in here like I do in mechanics where there's a fake 1 there and all that garbage, right? We're advanced enough. Because they still, every single time, I have to say that in there. And still some of them go, I don't understand, Mr. Chilton. But yeah. How many times do you have, Corbin knows this. How many times do I have to say, remember there's a t to the 0 power right there? Every time. And there's still people in the room who are like, what? You're in 5th period now, so you see it all. Yeah, every time. Mr. Sheldon, what? Where'd the t come from? Mike, you know exactly what I'm talking about. Yeah. Well, and how many times we've done it? 100? This year's just bizarre. It's a bizarre group. So you guys were in there last year. It is not the same this year. Not the same. What is the antiderivative of the inverse? Yay. So ln of v evaluated from the square root of 2gh to some value in the future. All right? All right, getting pretty close, aren't we? This isn't done, although we're getting close. We're going to put in our boundary conditions and get negative c over m times t equals the natural log of v over the square root of 2gh. Now, there's no chance the value that's in the brackets there in the absolute values is going to be negative. Even though the square root there suggests plus or minus, we know that only is going to be the positive option. But the absolute values are holdovers, so I continue to use them. We want to solve this for v, which means raising both sides to a base of e. And then multiplying across your boundary condition. All right. Is that our answer? No. If you leave it here because you're in haste, you'll be in trouble. We need to sub back in what we got for C. So go back up to the top. Remember that you have to put in what you have for C. And this produces an answer that is, I agree, a mess. When you guys are actually writing this on your exam next, please be as careful as you can. about the way you write it. Make sure what's supposed to be in the exponent looks like it's in the exponent. Some of you, your handwriting is going to lose points for you because it's unreadable. I have some. Any questions about this? Does this ever go to zero? And you guys are in calculus now. You understand that it does go to zero as t goes to zero. You understand that? I'm sorry, as t goes to infinity. Right? You've been learning that in calculus. You get the idea of the limit of a function. I want to remind you that in real life, the bar will stop for sure because there will be other forces acting on it. But there's also the idea that even if you could make it perfect, the bar is going to reach a point where it's traveling so slow as to be imperceptible. So zero is kind of a nebulous concept. I'm not saying that it's fuzzy in any way, shape, or form. I'm not saying it's not true. What I'm saying is that infinity is not as far away as you like to think, at least not in the context of these problems. But look at what controls what happens here, right? Because you're going to be asked questions, and your ability to understand what this function does is valuable. Do you understand? And think about it in your head. If you make the magnetic field bigger, would you expect it to stop sooner or take longer? Now, I would expect it to stop sooner for a number of reasons. The first one, if the magnetic field is bigger, we get a bigger EMF produced, right? And if we get a bigger EMF produced, that would produce more current, and more current makes the force on the bar greater. So 2 factors, thus it's squared. Same with L on the bar. L determines the amount of area that's changing. A bigger L, bigger change in area, bigger EMF. L also is in the function that covers the force. So a bigger bar, larger force. So L is squared. Every point that's there can be talked out as to why it's there. Interestingly enough, M is in the denominator. Why? Bar will have more inertia. Because it has more inertia, it will be harder to stop. So it will take longer to stop. Does all that make sense? Now, I put an R there. What was in the original thing? Was it R? Yeah. Oh, capital R. Yeah, the resistance. What am I thinking? What am I thinking? Radius? Now, the resistor one's a little bit harder to come to grips with. Can you kind of understand why the R is there? Same EMF, larger resistance produces less current, right? Less current means the force on the bar is less, it will travel further. So every one of those variables, you can go back to something physical about your original scenario and explain why it is the way it is. At least you should be able to. Look at the way they're connected, be able to explain it. Now, I don't want to spend a lot more time on this, but this will go to zero for a long enough period of time, a long enough function of time. But this is how we solve our differential equation. How many of these steps do you have to show? You have to show as many, I'm trying to get back out to where we first created the differential equation, so that would be here. You have to show enough steps here to do 2 things. Indicate that you're starting from a first principle, F equals ma. Make sure you set up your integral. I don't know that you can go from here to here. If it were me, and they'll likely require it, you should stop at some point where you have a differential equation. But you can go from here to here. They don't need to see your algebra. This establishes that you understand the boundary condition. And then you could jump from here to here. You don't have to show any of that math. There will be no point awarded for the math that takes going from the integral symbol to your result. Just isn't any point. If at best, 1 point for doing all of your calculus and algebra all together. So the number of steps you show is on to you. Derive doesn't necessarily always mean the algebra. Derive often means starting from a first principle and doing appropriate substitutions. But the algebra, the number of steps you take is on you. You may or may not have enough time to write out every step. It'll be a choice you make. Now, you screw up your algebra because you don't write every step and you get the wrong answer, you throw the whole thing away. So there's a trade-off there on how you budget your time for a question like this. A couple of things to consider here. Power is the rate at which work is done. Work is the integral of force dot dx. Bringing up different things because clearly there's a force in the bar that does work. And its net work, this will be the change in kinetic energy. Power is also defined as I squared R. These are all the definitions. Right, so in this function, we have I squared R. We also could define it as EMF squared divided by R. We have a function for the EMF, correct? I mean, way back when, and all of this, we have a function for the EMF. But that function has V in it. Right, you see that as well. So if we were, now that we have V, we can express the EMF in terms of the function that we have for V. Well, that squared times R, divided by R, is going to be the power dissipated. Meaning I could write power as, help me out here, B squared L squared times 2GH e to the minus 2 B squared L squared over MRT divided by R. Right? This equals dW dt. This suggests if you want to find the total work done by the magnetic field, you could integrate this from 0 to infinity, and it would give you the total work done. Look at the future of this. When you go to integrate this, this term is going to pop out of the integral, right? But it's going to be the inverse. You're going to add 1 to the exponent for e because you have to do u sub on the e function, right? You know what u sub is? So you will eventually be dividing this function by b squared L squared mr. Do you understand that that's going to take away this b squared L squared and r, leaving you just with m over 2. GH, do you see the formings of a 1/2 mv squared in here or an mgh in here? Because I'm starting to see the formings of that. Pretty confident the 2's are going to cancel out. I'm going to be able to put an m in there, and I will get mgh as the amount of energy. Now, I'm not going to do the integration here. We could, and it would not be that hard, but some of you can't handle 2 of these in one particular day. But you should think about trying it on your own. This might look like a very challenging integration, but almost all of it's a constant. The integral actual function is e to the minus ct. That's the only thing you'll be integrating. If you can get past the algebra, that's it. And you're integrating the function of e from 0 to infinity, which is going to give you a 1 minus 0 as your functional integral. But it's going to pop out a constant. And I bet that constant cancels everything out except for mgh. Guaranteed. If you don't believe me, try it. You should do it. Me doing it doesn't serve as good a purpose as you trying it. So you try it first. If you come at me showing me you tried it, I'll perform it so you can see it done. But this will equal, when you integrate, you find the total work done, it will equal mgh, where the bar started. I didn't make up this problem. This has been on the AP exam. And they did ask how much energy was dissipated by a bar as it slid across the rails. And people would do all of this. when all they had to say is conservation of energy, it started with MGH, that's how much energy is going to have to be dissipated by the magnetic field. It's going to be conserved. But you should try it, prove it. So just to be thorough, and although we didn't do this in class, I think it's appropriate. Does it really equal MGH? So we take dW and split the differential. We have our, it's a mess, but hear me out. B squared L squared times 2GH e to the minus 2 B squared L squared over MRT all over R dt. And this is not great. Let's make it a true exponent so it doesn't look like I'm multiplying. So negative B squared L squared 2 B squared L squared. Come on, Eric. Negative 2 B squared L squared over MR T. I want to integrate this 0 to infinity. Everything about this is a constant. So we'll get B squared L squared times 2GH over R. That pops out of my integral. Then I just have the integral of e to the minus 2 B squared L squared over MR dt. dt, again, evaluated from 0 to infinity. So, B squared L squared times 2GH over R. This antiderivative will be M over R divided by 2 B squared L squared, it's a negative sign too, times e to the negative 2 B squared L squared T divided by MR evaluated 0 to infinity. All right, so let's do a little bit of reduction. R, B squared L squared, B squared L squared, 2, 2. So I have negative MGH e to the negative infinity minus e to 0. And this is the total work. So 0 minus 1 gives me a negative MGH. So work will equal MGH. Oh wait, that's what we said. That's the total energy we had. It has to work this way.